In video number 2, we are going to cover pages 379 to 381 in the book. We're going to skip page section 19.3 about molecular mass determination. That's not all that important. So in section 19.4 in the book, it's mass to gas volume and gas volume to mass. Okay, so there's a really helpful conversion to know, and that is 1 mole of gas occupies 22.4 liters when you are at STP. What do those initials stand for? They stand for standard, temperature, and pressure. Well, what is standard temperature? Standard temperature is 0 degrees Celsius. Standard pressure is 1 atmosphere, which is the same as 101.325 kPa. So we like to standardize our experiments, and so scientists will very often carry out experiments at standard temperature and pressure. If I were to use the ideal gas equation, and I was going to solve for volume, PV equals nRT, suppose I had 1 mole of gas, okay, 1 mole, and I was at STP, and I was going to solve for volume. Well, nRT over P, and then I plugged in 1 mole, I times it by R, multiply it by my temperature, which is 273 Kelvin, because you always have to do your temperature in Kelvin, and I divide by my pressure. Well, guess what this volume turns out to be when I plug it into my calculator? 22.4 liters. So if I have 1 mole of gas, it will occupy 22.4 liters when I'm at STP. So that's a super handy conversion to use, because if I had twice as many moles, if I had 2 moles, well, then I would know that my volume would be twice as big, and I wouldn't have to go through all of this calculations and writing stuff down. So that's what section 19.4 is all about. It's about using this handy-dandy conversion so you don't have to go through the ideal gas equation. So here's a problem. How much volume would 2.8 moles of oxygen gas occupy at STP? And again, the key is that you are at STP. If you are at STP, then you can use this conversion. 1 mole is equal to 22.4 liters. If you're not at STP, then you must use the ideal gas equation. But if you're at STP, the problem comes a lot faster, because you have to say, okay, I got my moles, and then you just do railroad tracks. 1 mole will occupy 22.4 liters, and you just multiply the two together, and there you go. And I get this answer, and with 2 sig figs, it'd be 73 liters. Okay? This is called going from moles to volume. Okay? What if we want to go the other way, and we wanted to know how heavy would 125 liters of helium gas weigh at STP? Okay, let me write that a little bit better there. Actually, can we make it nitrogen gas? Okay, how heavy would 125 liters of nitrogen gas weigh at STP? Okay, so we're going to do the same process as above, but we're going to work it backwards. I've got 125 liters. I'm at STP, so 22.4 liters gives me 1 mole, all right, of nitrogen gas. I'm adding one extra step on here, and that is I want to know grams, okay? So right now, the liters cancel, and I'm stuck with moles. Well, I know it's been a while, but we want to convert our moles back into grams. So how much does 1 mole of nitrogen weigh? Well, nitrogen weighs 14 grams, and there's 2 of them. So the molar mass of nitrogen is 28 grams. So now I can plug it into my calculator, and I get 0.1, whoops, no, I plugged it in wrong. That's why we show our work. It would weigh 156 grams. Okay? This would be helpful if you're trying to figure out how heavy a fire extinguisher would weigh with compressed carbon dioxide. Okay, let's just do one more example of this. Let's go backwards again. Let's switch it up and say, how much volume would 240 grams of carbon dioxide occupy at STP? So I've got my 24 grams of carbon dioxide. I can write that better. So we're going to convert this to moles. So carbon weighs 12, oxygen weighs 16. There's 2 of them. So we add that up, 44. So I know it's been a little while. I kind of did that a little fast. So carbon, you look on the periodic table, weighs 12. Oxygen, you look on the periodic table, it weighs 16, and you multiply by 2, and you get 32 and 44. So 44 grams goes on the bottom. Notice how I label everything nicely? So the grams cancel. Now I've got moles. For every 1 mole, it'll occupy 22.4 liters. Okay? Now, for whatever reason, the book likes to use decimeters cubed. Okay? A decimeter cubed is the same thing as a liter. Okay? So if they report in the back of the book as decimeter cubed, so be it. Okay? So, you will have to, in let's see, in the homework, you need to convert centimeters cubed to liters. I'll just review that after I do this calculation here. So 24 divided by 44. This is 12.2 liters of carbon dioxide gas, or I should say decimeters cubed. Okay? So if the problem gives your volume in cubic centimeters, you have to convert to liters or decimeters cubed. So 1,000 centimeters is 1 liter. So I think it's just easier to convert it to liters. So if the problem gives it to you in any other unit, you have to convert to liters.